Welcome back to the end of chapter 19. A few more slides and then we'll be done. I've taken this opportunity to actually emphasize and draw parallels to many things you already learned in Orgo 1. So we're almost done with this chapter, and as we are moving forward, the first topic to be introduced here is the Baeyer-Villiger oxidation reaction. This is something in which you can look at having to have a carbonyl group first, and here is RCO3H. This is a per-acetic acid. Remember how acids are usually R, C, O2H, but here we have an extra oxygen, yeah? And basically, we're transferring the oxygen, we're inserting it into the carbon-carbon bond here. There's a mechanism shown. It's a more unusual mechanism. I will not spend time on this. If you want to pause and work your way through, then that's okay. Bottom line is an aldehyde or ketone is converted to a carboxylic acid for aldehyde or an ester for a ketone. The other beneficial aspect about this transformation is that when we have a cyclic ketone, we can actually make a cyclic ester. And guess what? Esters will show up in our carboxylic acid and derivatives chapter 20. When this portion is cyclic, and here we have symmetry, we form what is known as a lactone. If for an aldehyde or an unsymmetrical ketone, we now talk about the rate of migration. What does that mean, the rate of migration? This structure here is symmetrical, but what if it was unsymmetrical? The reason why we have insertion into carbon-oxygen bond is because of that very important migratory step. So, rate of migration is highest for hydrogen, then tertiary, then secondary. Phenyl over primary over methyl. So this trend now helps us to understand regioselectivity. All right, here we have a couple of examples. See how this is unsymmetrical. We have an isopropyl group on the left, and we have a methyl group on the right. It now means that the oxygen, remember extra oxygen here of our per-acetic acid, is going to go to the side with the higher substitution pattern. And here we are. When we have an aldehyde, here basically we're inserting into the carbon-hydrogen bond, and then it becomes a carboxylic acid. Again, that's going to come up in chapter 20 as we take a different perspective from that functional group there. So it's basically repetition when we get to that in chapter 20. So now the bigger picture, and I understand students often become quite overwhelmed with all this information. We want to keep our gaze on the connectivity of the structures. So, when designing a synthesis, and in Orgo 1 you had a whole chapter devoted to synthesis, and that was chapter 11. Question is there change in the carbon skeleton? Are the carbons in the same sequence? Has something changed here or rearranged? Is there change in the functional group? So one of these reactions will be needed when the carbon skeleton is changed. We had talked about the Grignard reaction, using a Grignard reagent that gets this all going as a carbon nucleophile. We discussed in this chapter the nitrile via now the formation of the cyanohydrin in here. And we talked about the variations of the Wittig reaction, and see how the carbon-oxygen double bond in each of these, coded red, C, C, and C, we've added, right? We have it highlighted here, here, and here. So it's always very helpful to get an overall view as to what has changed, and that then can help us make a decision as to which reagents we're going to use to synthesize molecules. Here's a more a broader overview of synthesis strategies. In Orgo 1, you learned all about interconverting single to double to triple bonds and back, lots of reactions. Alkene addition reactions included making alcohols and halides, all Orgo 1 material. And now we've graduated to Orgo 2 material, carbonyl groups, aldehydes and ketones, many, many reactions. And practicing the skill will help you clarify what is going on. Once you see the patterns, you will feel less overwhelmed, but it's really important to see the patterns. Spectroscopic analysis finishes out the chapter. This is review of what we had basically done at the beginning of the semester. That was chapter 14, ion mass spec, and chapter 15, proton and carbon NMR. So remember how conjugation is going to change the bond order, and we will see a certain shift. When we have ring strain, that can also afford these areas. If we take an electronic approach, we can make logical deductions and come up with the answer that is needed for problem solving. IR spectra, we had drawn 2 vertical lines at 3000. Let me see whether I can do this freehand. Nope, let me try again. I want to get to the 3000 here. Use your ruler. And then there should be 1 second vertical line around 1500. We look at the diagnostic region first, which is larger than 1500. So look, it helped that you studied IR spectroscopy. You get to use those skills again. And we had determined certain regions for the aldehyde. This is really very, very key. These 2 peaks here for the hydrogen that's attached to the carbonyl group in the aldehyde functionality. In this structure, we only have saturated CH stretches, which is responsible for the rest of the structure here. And then, of course, we had said that the polarization of the carbon-oxygen double bond makes this typically a good size stretch for the carbon-oxygen double bond. We can also look at spectroscopic analysis. Protons neighboring a carbonyl group are weakly de-shielded by the carbonyl group, and we usually have a downfield shift. Downfield means to the left, and so you can practice this again by looking at some chapter 15 material. If you have great notes, wow, now you just look at your notes and you can just quickly look up the information. So, the difference between these 2 structures, methylene group, CH2, methylene group, CH2. But this one has the carbonyl group. Remember, there's resonance, it's electron withdrawing. We use the same concepts again, thus there can be a de-shielding effect. And guess what? The presence of that carbonyl group makes these hydrogens in the alpha position very special, and we have a whole chapter dedicated to a lot of rich chemistry, and that's chapter 21, alpha carbon chemistry, enols and enolates. An aldehyde proton is very de-shielded. Here you have an example. Again, we have an electron withdrawing group. Remember, multiple bond, we can delocalize electron density through resonance form, which is a stronger effect than induction. And here we are. We see a very significant peak in an area where usually there are no other peaks, and that's between 9 and 10. And then we look at carbon 13. We see a similar effect. It's just on a different scale here, from 0 to over 200, because this can be opened up, positive charge here, negative charge here, highly de-shielded, shift downfield to the left, and so we have a weak signal near the 200 region. And here we are, lots of reactions, lots of information. I hope you get something out of this video, and keep on practicing.